This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We have an interesting problem here. We're going to use the dot product, which gives us vector projections, to solve for the components of a force, a vector, the components that are parallel and perpendicular to a line. Here's my setup. I have force F, 2I, negative 3J, 5K, the units are pounds. It intersects this line, the x-axis at the point C, which is coordinates 5, 0, and 0. We don't really use that for this problem. And I have a line in space with 2 points given on that line. Point A is at coordinates 0, 9, and 8 feet. Point B is at coordinates 9, 6, and 0 feet. And so, as I say, I want to resolve vector F into the two components parallel to line AB and perpendicular to it. I'll show it kind of cleared up down here. First thing I need to do is get a position vector. What I'm driving at is getting a unit vector in the direction AB. So the first step is getting a position vector RAB. I could also get a position vector RBA, and the signs will reverse, but my answer will be the same. So I picked RAB. A is the tip, B is the tail. I subtract the coordinates of the tail from the tip. So I get 0 minus 9 in the I, 9 minus 6 in the J, 8 minus 0 in the K. Writing that all out, negative 9I plus 3J plus 8K. Units are feet. I want to get the length of position vector RAB, which is a part of the steps of getting UAB, unit vector. The length RAB is the square root of the sum of the squares. 9 squared, 3 squared, 8 squared, square root of 154. It's equal to 12.41 feet. Now UAB, the unit vector, which I've shown in blue here, is just the vector RAB divided by the length of RAB. Negative 9I, 3J, 8K, divided by 12.41. Doing all the math, I get negative 0.725I plus 0.242J plus 0.645K. Now, that is a unit vector in the direction of AB, line AB. Next step is to get the dot product to give me the F projection, which is just a scalar number. It's really the length of the line. So that's just F vector dot UAB vector. Here is F, 2I, negative 3J plus 5K. Here is UAB, expressed as Cartesian vector. I just multiply the I terms, the J terms, and the K terms together in this manner. 2 times negative 0.725, and so forth. And I get these numbers that I just add up algebraically. Negative 1.45 is 2 times negative 0.725. And these are the other two terms. Add them all up. I get 1.049 for F projected. So that is F, the vector F projected on line AB. So I want to express that as a vector, so I just multiply the scalar number F projected times my unit vector UAB. 1.049 is F projected. Here's UAB from up here, and I'm left with the vector F projected in Cartesian format is negative 0.760I plus 0.254J plus 0.677K, and that is the vector of F projected on line AB in Cartesian form. Now, I also want to know, so that's half of my answer. I also want to know what the vector that's perpendicular to line AB. So I use this relationship. And it helps me to think about it to move line AB, which is just a line, really a direction in space, over here so that it intersects, move it to point C, so that that line intersects that point. Then I can show this vector relationship where F is the resultant vector, F parallel, those should both have little lines over them to indicate that they are vectors. I have F parallel vector to AB, and I have F perpendicular to AB. It's hard to show these things in 3 dimensions, but these vectors are perpendicular to one another. I've shown that with this perpendicular sign. So, F is really the resultant of F parallel plus F perpendicular. So I can subtract F parallel from both sides of this equation, and I get that F perpendicular is equal to F minus F parallel. Well, subtracting a vector from another really means adding the negative vector. I guess I'm rubbing my hand on the drawing. So it's equal to F plus the negative of F parallel vector. So I can write F parallel that I just calculated up here, negative 0.760i, 254j, 677k. Then to get the negative of that, it's the reverse direction. I can just reverse all my signs. So that's positive 0.760i minus 0.254j minus 0.677k. Then I rewrite vector F right below it, so I can just add the columns, and I get that F perpendicular is equal to 0.760 plus 2, or 2.76i. Add those two, which gives me a negative 3.254j. Add those two numbers, I get 4.323k. Okay, I want to check myself using Pythagorean theorem, square root of the sum of the squares. And so F parallel squared, the scalar value, plus F perpendicular squared should be equal to F squared. So I already know that F parallel has this F projected scalar value of 1.049. So that's the length of F parallel. I can figure the length of F, the vector that I started with. Square root of the sum of the squares is square root of 38, or 6.164 feet. And I can get the length of F perpendicular, the square root of these squares, some of these squares. So do all the math. The length of F perpendicular is 6.074. So I check that F parallel, which is 1.049 squared, plus F perpendicular, scalar magnitude is 6.074 squared. Take square root of that, 6.164, which checks out to be the length, scalar magnitude of vector F. So I feel good about my calculations. Now I didn't ask for it up here, but while we're at it, we may as well illustrate the use of dot products to get the angle between two vectors. So if I want to know the angle between vector F and line AB, it's just the dot product of F with UAB. I've already got that number up here, and that's equal to F, the scalar, times U, which is 1, the length of 1, cosine theta. So cosine theta, rearranging, is equal to the dot product of F and UAB divided by the scalar magnitude of F. So theta is equal to cosine inverse of that divided by F. Plugging in numbers, theta is equal to cosine inverse of 1.049, which is the dot product of F and UAB from up here, divided by the vector length, the scalar magnitude of F, 6.164. Plug it into my calculator, 80.2 degrees.